Two particles move along the x-axis. For 0 is less than or equal to t, which is less than or equal to 8, the position of particle p at time t is given by x sub p of t equals the natural log of t squared minus 2t plus 10, while the velocity of particle q at time t is given by v sub q of t equals t squared minus 8t plus 15. Particle q is at position x equals 5 at time t equals 0. A. For 0 to 8, when is particle p moving to the left? So we have two particles, p and q, so make sure you are working with p. When they ask for p, working with q when they're asking for q. Mind your p's and q's, in other words. Do they still use that expression? A is a classic particle question. I want to know when particle p is moving to the left. Particle p is going to move to the left when its velocity, in other words, when the derivative of the position function is negative. Then it's going to move to the left, or down if we were in an up-down situation. So remember, when your velocity is negative, that means you're moving to the left. So all we have to do is take the derivative of p, of this position of particle p, and then find its critical point and see when the velocity is negative. Derivative of natural log is 1 over that thing times the derivative of that thing. Chain rule. Okay? There's my velocity, okay? Derivative of the position. I'm going to find a critical point. Critical points happen when your derivative is 0 or undefined. Let me just write it like this. If you want, you can cross multiply or just imagine, hey, you know, this fraction is going to equal 0 when the numerator is 0. That's going to happen at time equals 1. So that is your critical point. Now we should quickly ask, is this the only critical point? Remember, critical points happen when your derivative is equal to 0 or undefined. Since we have a fraction here, we should really look to see if there are any times where the denominator is going to be 0. But I think a quick analysis will tell us that on the interval that we're interested in, from 0 to 8, that will always be positive, right? So that denominator is going to be greater than 0 for the numbers that on my interval that I'm interested in, right? So I don't have to worry about any critical points where the derivative is undefined. It's easy to forget that part. Let's set up a number line, a number line, a number line. When you're doing a number line, please very carefully label it. In fact, I should have put a little p there, a little sub p. Label it. So my critical point is when time is 1. I know my velocity is 0. You're going to pick a value underneath it. Maybe 0 is handy. A little above it, maybe 2 is handy. So I'm going to plug 0 into my velocity here. That's going to be 2 times 0 minus 2 over 0 squared minus 2 times 0 plus 10. You don't have to write this part out. I'm just doing it. The top is negative. The bottom is going to be positive. So that gives me negative velocity, negative velocity, negative velocity. Now let's plug in 2. I think you can probably quickly see I'm going to get something positive now. I'm going to get something positive. You can use your calculator for this if you want. Okay, so what does that mean about particle p? That means particle p is moving left from 0 until 1 second. Did they give me time? No. So I don't know what my units are. But particle p is moving left from 0 to 1 time increments. then it turns around and it's moving to the right. So this asked, on the interval 0 to 8, when is particle P moving to the left? And it is moving to the left then on the interval from 0 to 1. Okay? Now, in terms of equal or not equal, you can put t is greater than or equal to 0 because, you know, that's when we started. But generally, if we're talking about moving in time, you don't want to include 0, you don't want to include 1 because at 1, the particle actually stopped. B, for times 0 to 8. Find all times t during which the two particles travel in the same direction. Now B is going to build on this work. B is asking, when are the two particles traveling in the same direction? Okay, so I have to do this same process, but for Q, they gave me the velocity, so I don't have to take the derivative, so that's handy. I just want to find the critical points of Q, and maybe I can just do that right up here. So the critical points of Q will be when that velocity equals 0 or is undefined. There's no time, this is going to be undefined. I'm going to factor this. You could use your calculator, obviously, since you're allowed to have one. Okay, so I have two critical points. I have a critical point at 3 and a critical point at 5. So you know what I'm going to do? I'm going to put my number line for Q above my number line for P and kind of line it up so I can compare and contrast. So I've got 3 and 5. I'm sure we can see all that. Okay, I know my velocity is 0 at 3 and 0 at 5. So let's plug in some values. And I'm going to plug things into the factored form. You don't have to write this out, but I'm just doing it so you see what I'm doing. Plugging in 0 into the velocity, that's going to give me something positive. So I know particle Q is moving to the right from 0 to 3. Let's plug in 4. If I plug in a 4, 4 minus 5 is negative. 4 minus 3 is positive, so that's going to give me something negative. Let's plug in 6. That's going to give me something positive. So I'm moving to the right. Q is moving to the right from 0 to 3. It's moving to the left from 3 to 5. And then it's moving to the right again. So the question is, when are particles P and Q moving in the same direction? So this is when we can line this up. So they're not moving in the same direction from 0 to 1, but from 1 on, they're both going to the right, 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 until 3, it looks like. So I think they're moving in the same direction from 1 to 3 minutes or seconds. And then it looks like I'm moving to the left up here, moving to the right here. So not until 5. Okay, so P and Q are moving in the same direction. P and Q move in the same direction on the interval. And you can do this with interval notation or with greater than or equal, 1 to 3, and on the interval 5 to 8. And I guess since 8 is our endpoint, we would do that as an inclusive bracket. I don't think that's all that important. But we do have to say y, and that's since x prime sub p of t and v sub of q have the same sign. So particle P and Q move in the same direction from 1 to 3 and from 5 to 8, since they both have the same sign. Okay? Very nice. C, find the acceleration of particle q at time t equals 2. Is the speed of particle q increasing, decreasing, or neither at time t equals 2? Explain your reasoning. C asks us for the acceleration of particle q. Well, acceleration of particle q, of course, is just going to be the derivative of the velocity of particle q. That's not hard to take. We want to know the acceleration at time 2, so that's not a big deal. That's going to give me 4 minus 4, -4, whatever my units are. Now, the next question, is the speed of the particle increasing, decreasing, or neither at time t equals 2? So let's remember, a particle's speed is increasing when the velocity and the acceleration have the same sign. So, in other words, if my velocity is positive and my acceleration is positive, I'm speeding up. If my velocity is negative, going to the left, and my acceleration is also negative, I'm speeding up. The particle will slow down. The speed decreases only when the velocity and the acceleration have opposite signs. Okay, so I want to just know specifically at time equals 2, is my particle speeding up or slowing down? Well, I know that my acceleration at 2 is negative, and let's just find what my velocity at 2 is. 2 squared minus 8 times 2 plus 15. You don't have to show this part. That's 4 minus -12. That's going to be positive. I think +3 if I did my calculations correctly. So here we go. My velocity at 2 is positive. My acceleration at 2 is negative. So at time equals 2, Q is slowing down since A Q of t, A of Q of 2, and V sub Q of 2 have opposite signs. And there you go. Now just for fun, let's say that the question had instead just been, find the interval where the particle is speeding up. Right? Then you would have had to do what we did many times in class, where you create 2 number lines, one for the velocity, one for the acceleration. Remember this? And you find when the signs are the same. So let's see, the signs of the velocity and acceleration are opposite, so the particle would be slowing down from 0 to 3. Ooh! The particle would be speeding up from 3 to 4, and again speeding up from 5 on. So they did not ask us this for this question, but if they had, this is how you would have determined the intervals on which the particle was speeding up or slowing down. D, find the position of particle Q the first time it changes direction. So for D, I'm looking for a position at the time when Q turns around. Well, when it first turns around. Well, that we already figured out. From our previous work, we know that particle Q is moving to the right, and then at time 3 it turns around and goes to the left. So I'm looking for the position of this function at time 3. So to find a position from a velocity, I need a starting position, and I need to take the integral of that velocity, which will give me my change in position, or my displacement. This is the fundamental theorem of calculus. So the position of particle Q is 5, because the problem told me at time 0 my position is 5, plus my change in my position from 0 to any time t. Since I want to find this at time equals 3, I'm going to replace that t with a 3. Now I'm going to take the antiderivative of the velocity function, which is not that difficult. Antiderivative of t squared is 1/3 t cubed. Antiderivative of 8t is 4t squared. Antiderivative of 15 is 15t, and I'm analyzing that from 0 to 3. And then I just have to do the plug in the 3 and plug in the 0 and subtract. So let's get our final answer. If you plug in all of those, you'll end up with 23. So the position of particle Q at time 3 is 23. In other words, 23 units to the right of the origin. How fun was that?